Justin Miller, Epsilon College Physics. We want to now start looking at some circuit elements. And the first one that we're going to look at is one of bundle of energy, we'll say. All right, so let us just consider something first that we've considered and go from there and introduce some new notions here. So we've looked at charged sheets, right? And we note that if we place the sheets parallel to one another, we've got ourselves an electric field between the sheets. They're equal and opposite charges, and that electric field is uniform. We get all sorts of nice things. There's a potential difference between the sheets. There's a spatial separation. So kind of draw something out here. I'm going to take two sheets that are facing one another. And have an equal and opposite charge uniformly distributed over the sheets themselves. Say across these conductive sheets. So, what do we have here? We've got a sheet, and it's got some surface charge density plus sigma, right? Which would mean that, hey, it's a bunch of excess positive charge. And we've got another sheet. Let's stick it over here, facing the sheet, and say this one has a surface charge density of minus sigma. Great. And it's got an excess of negative charge. And what do we know about these? Well, we could draw out some stuff, right? We've got that these two sheets are separated by some distance. Distance of separation, d. We would have that there would be an electric field between these sheets. Now, I'm not going to worry so much about edge effects. There would be some edge effects where you get some bowing. We'll just go ahead and say that these sheets are close enough to one another where we can approximate the electric field as being uniform, even though that's not super important right here. We just kind of want to draw it in. So we've got this electric field in between these sheets, points away from positive towards negative. So we've got yourself some E hat there between the sheets. And what else do we have? Well, if we got an electric field, we're going to also have ourselves some potential difference across these sheets. Delta V. Potential difference across the sheets. What else do we have here? Well, we can go ahead and say we'd have some total charge Q and minus Q. So plus Q and minus Q. It would be the same amounts of charge, just opposite, right? So what do we have with this? Well, this is it. We've got some potential difference that correlates with the displacement within an electric field. We've got these charge accumulations on either side of the sheets, and we get that these sheets are separated by some distance. So what, you may say? I say, well, that's what we got. Is there something that we can kind of think about with this? The answer is, yeah, we can think about some stuff. Like, what happens if we double the amount of charge? What if we double? amount of charge on both sheets. So we add another plus Q on this side, so we'd have plus 2Q, and we add another negative Q on this side, so we got negative 2Q on this side. So have equal and opposite amounts of charge. What changes? Well, the distance of separation, we're going to keep that the same. We'd have that the electric field definitely changes, right? It gets stronger because we've got more charge producing it. And if the electric field is getting stronger, then the potential difference between the plates would also increase. So what it turns out here is that that increase in the potential difference, regardless of how the electric field behaves, that increase in potential difference is directly proportional to the amount of charge that's separated. We double the amount of charge separated, we double the potential difference across the plates. So what we find here is that delta V is proportional to Q. And if it's proportional, that means that there has to be some constant proportionality between the two, right? So you may say, well, okay, what's the constant of proportionality? And what does it depend on? Well, there is a constant proportionality, and it depends on a few things, like the distance that these sheets are separated by, the surface area of the sheets, the contour of the sheets. It can depend on a lot of different things. But those are all geometric things that it depends on. Shape of the sheets, the area of the sheets, the spatial separation. The fact that these two things are proportional to one another should make sense. Like more charge, greater potential difference. There we go. So we go ahead and define a new quantity here. Let us define, that was not even close. Let us define constant of proportionality as C. We're going to call this the capacitance of the system. Such that Q is equal to C times delta V, where Q is the total charge separated, and delta V is the potential difference across the plates. So that we can write that C is defined as Q divided by delta V. Total charge separated divided by potential difference across the plates. So this is how we define this constant of proportionality. The ratio of the charge that's been separated divided by the potential difference across the plates defines the capacitance of the system. So we're just defining something else. So what's good about this? Well, take this for instance. What would happen if I connected this plate and this plate with some conductive pathway, like a wire, connected them together? Well, there would then be a pathway for this charge separation to neutralize itself. Charge doesn't like to be separated. Positive, negative charge doesn't like to be separated. These electrons we can think of as coming from the sheet because they're in equal amounts. We have exposed protons here because we took off electrons and stuck them over on this plate. So they have equal amounts of charge. And that's our charge separation, Q. So what happens if I put a conductive pathway? These electrons, being that they're on a conductive sheet, have the ability to redistribute themselves. They're attracted to all these protons. So what happens? Whew, they sweep over here, and they cover them up, and it neutralizes the system. But in them sweeping over, there is electrical energy. That's the flow of charge. We'll get to defining that a little bit more, but the main thing is that there's energy stored in this system. Energy stored in this charge separation. And hey, that's it. That's what we've got going on. So that is important because we can start to build electrical circuit elements that have very similar types of constructions that do just that, store energy that we can use at our bidding or to do certain things. All sorts of uses. But what do we call it? Call them capacitors. We can build capacitors, which are ultimately two plates that face one another, for which you can take electrons off of one plate, stick them on the other plate, store a charge separation, and there you go, you got yourself a charged capacitor. And we'll get to how we get the electrons from one plate to the other. That's to come. Right now we just want to focus on the system right here. So, what do we do with this? What do we do indeed? Well, here is your kind of run-of-the-mill capacitor. It's got two terminals. It's got a positive and a negative terminal, and it just looks like some little cylinder. Well, this isn't two parallel sheets placed next to each other. This is a cylinder, but there's an outer cylindrical sheet and an inner cylindrical sheet, and they're ultimately connected with these little wires here. And what we can do is we can take electrons off one sheet, put the electrons on the other sheet, so we have a positive sheet and a negative sheet facing one another, and hey, that forms a capacitor. If we have the charge separation, it's a charge capacitor. What can we do with it? Well, inside this little camera, this little flash camera, old disposable one, there is a capacitor. And what I'm going to do is I'm going to charge that capacitor up. And you say, how are we going to charge it? I'm going to do it with my mind? No, there's actually a battery in this camera that's going to do that for me. So the battery is a source of potential difference which can make charges move, basically sets up an electric field. So this battery is going to take electrons off of one of the plates of the capacitor that's inside and put it on the other plates. And then I'm going to stop charging it, it's going to be charged, and then we'll try to release the charge and see what happens. So let me just go ahead and touch these wires together right here. These two wires are connected to the terminals of the capacitor that's inside here. It's a smaller capacitor, but it's a capacitor nonetheless. And how do I charge it up? I hope I can press the little, hey, let's get the capacitor charged up button to charge up the flash. So you won't be able to hear this, but usually it makes a little sound just so you know that it's charging. All right, maybe you heard the sound, maybe you didn't, but it stopped. I heard it. It means it's charged up. So that's great. That's great. What can we do with that? Well, now that it's charged, I can connect these two wires together and produce a conductive pathway in between those two charge sheets. What's going to happen? The electrons on the negatively charged sheet are going to sweep back over to the positively charged sheet and neutralize that charge separation. So watch what happens. Oh, whoa, my gosh, did you see that? Shocking, right? Shocking. What happened? There's a little ionization of air because as these electrons were rapidly jumped over, they jump a little gap, they run into some air molecules, ionize it, and you get this little flash. But that shows us, hey, there's energy that was released. And that's what capacitors could do. The general function of it in this system would be passing those electrons through this little flash bulb, and you get the flash. A nice rapid flash for when you take the picture, and you get some better exposure if it's dark. That's just one use of capacitors. They're all over in many different electrical types of systems. They're in keyboards, they're in old analog radio tuners, station tuners, strobe lights, the little lights that go on and off, on airplanes, all sorts of things. Capacitors all over the place, all over the place. And we find many, many different uses for them. We use them in memory banks as charged, uncharged, binary, on, off, zeros and ones, or ones and zeros, I should say. And yeah, they have lots of different uses. What we just want to do is be able to understand capacitors themselves. So at that, what we're going to do is we're going to focus our attention on a particular type of capacitor, which is known as a parallel plate capacitor, which is this kind of configuration here. We got two plates that have some area, surface area, they have some distance that they're separated by, and we place them facing one another. We take electrons off one plate, stick them on the other plate, such that we have equal and opposite charges, a charge separation, and then we got ourselves a charge capacitor. Boom, then we can release the energy or store it for later use, whatever we want to do with it. But the main thing is that we want to understand the capacitor. The parallel plate capacitor is the easiest one. There are many, many complex types of configurations for capacitor, but they all work on the same premise. Producing a charge separation between two plates that are facing one another. Oh, anybody ever used a defibrillator or had one used on them? I haven't, but if you have, okay, that's a shocking experience, it looks like. Anyways, the defibrillators, to get the rhythm of your heart going back to normal for arrhythmia, what happens? What do? They say, charged, and then they say clear, so everybody doesn't touch the person anymore, and then they put the paddles on their chest, and they get shocked, right? What happens? They're passing a little electrical current through the heart to try to get it to reset, not restart, but reset its normal beating pattern. But there's defibrillators. Those are capacitors. That's what it is. It's basically two capacitors. Now they're not facing each other, but it stills the idea that one's positively charged, one's negatively charged, and then that charge separation goes through your flesh, through your heart, and helps to restart things. Reorganize the beating pattern, I should say. Keep saying restart, no restart. All right, so yeah, let us take a look at parallel plate capacitors and kind of go from there. So give me 1 minute, I'm going to erase this off, and we can kind of restart. All right, so I want to look at some parallel plate capacitors. Parallel plate capacitor. Two plates, planar plates, that are conductive have a surface area A and a distance separation D. Two planar plates that are considered conductive have a surface area A and a distance of separation D. Which are placed facing one another. Form a parallel plate capacitor. That's kind of what we just drew in the preceding. And what we're going to do is we're going to use some approximations. The distance separation small compared to area dimensions. The electric field between the plates is approximately uniform. You have field between the plates is approximately constant and magnitude and direction. Magnitude of E hat is going to be given by what we go back and think about the connection between the electric field and potential difference, right? So before I write that, we just note that for a uniform electric field, we have the potential difference between 2 points within that field is equal to negative E hat dot delta R hat, right? So if we got two parallel sheets, we have that this can be construed as the distance between the sheets. Delta R goes to D, distance between the sheets. And well, we've got the electric field's uniform, so we've just got E stays as E. The negative sign we're going to absorb because we're only interested in the numeric value of the potential difference. The sign of it depends on whether you're measuring from the positive sheet to the negative sheet or the negative sheet to the positive sheet. So when we're just looking at the magnitude of the electric field between the sheets, we can write that delta V, absolute value, is equal to the magnitude of the electric field multiplied by the spatial separation of the sheets themselves. So that the magnitude of the electric field can be written as delta V over D. There we go. So what can we do with this? Well, we can do a few things with this because, well, there's other things correlated here. So let us do a couple things and think about what we've got going on. So I'll draw a little picture here, why not? We've got these two sheets here. We're separated by some distance D between them. We have a potential difference, delta V. Great. And we've got ourselves an electric field. We're saying it's going to go that way. It's uniform, constant in magnitude and direction, because this sheet has a surface charge density of plus sigma. This one has a surface charge density of minus sigma. We could say that this sheet here has a total charge, Q total, plus Q, and this one has a minus Q total because, well, this negative charge over here came from the positive charge here. And I guess we could draw that in, right? We've got 1, 2, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. There we go, there's the charges. We have Q's the charge separation, surface charge density, distance of separation, and lastly, should really be putting in, we've got ourselves E hat, points from plus to minus. There we go. So the electric field's magnitude is just given by the potential difference divided by the distance of separation. Great. And what else do we have? Well, we have by definition that C is Q total divided by delta V. Now this delta V is always considered to be positive. Q is always considered to be positive. You may say, well, he's got a negative there. Well, this is just the amount of charge that's been separated. Came off one plate, went to the other. This is the charge that's separated. This is the potential difference across the plates. We kind of drop the absolute value. Technically, it's still there. I guess we can kind of put it there, and there we go. So we've got those two things going for us. And what else do we have here? Well, we've also got that the electric field, if it is uniform, the magnitude of that electric field is associated with the surface charge densities, right? We got two sheets that we can start using the infinite sheet approximation because we're saying the electric field's uniform. So we've got that the magnitude of the electric field would be sigma over epsilon 0. Again, there's two of them. You add together, there's the overall electric field written in terms of the surface charge densities and the permittivity of free space. So we've got a few things going on for us. Great. let's go ahead and expand out on these two notions because we've got two separate identifying representations of the magnitude of the electric field. So what can we do with this? Well, from E is equal to this, E is equal to this, we've got ourselves that the potential difference divided by D, hey, that has to be equal to sigma over epsilon 0. All right, so what is sigma? Well, sigma, being that these are conductive sheets, sigma will be uniformly spread out, so it's a uniform surface charge density, and by definition, it will just be the charge divided by the area. Charge per unit area, there we go. So what happens if we put that in for sigma? Well, now we've got ourselves that the potential difference across the plates divided by the distance of separation is going to be equal to Q divided by A times epsilon 0. All right, that's pretty cool indeed. What else can we do with this? Well, look at this. We've also got this expression right here that correlates the total charge, the capacitance of the system, and the potential difference. So this right here can also be written as delta V is equal to Q divided by C. What happens if we put that in for this delta V here? So I'm going to go ahead and do that. We've got Q divided by C times D. Q divided by C times a D is equal to Q divided by A times epsilon 0. Just 1 second. So what does this do for us? Well, this allows us to go ahead and define the capacitance of the system totally geometrically, because we can get rid of these Q's here and solve this out for C. Solving for C, capacitance. Well, we move C over here, the Q's cancel out, and we move the A epsilon 0 up top, and we've got that C is equal to A epsilon 0 divided by D. That is the geometric description of a parallel plate capacitor. Parallel plate. There it is. We can define the capacitance in terms of the surface area of the sheets and the distance that those sheets are separated by. So there you go. The capacitance depends on the geometric configuration of the sheets themselves. And this is actually the case for any shaped capacitor. You can find some sort of geometric correlation with what the capacitance is. This is only for two parallel plates, where we've got planar plates facing one another. You start to look at cylindrical sheets that are wrapped around one another, you have a different capacitance. You have a different geometric description, but you can still find it. We're not going to do that. We're going to stick mostly with parallel plate capacitors, but again, there's all different types of shapes of the plates regarding, or I should say the surfaces regarding the charged sheets of a capacitor. This is just one. So we got this, right? Well, we've also got, by definition, C is Q divided by delta V. And that Q is the total charge that's been separated. That delta V is the absolute value of the potential difference. And with these two, you can again start kind of working backwards and seeing, hey, how everything reconnects. But ultimately, we've got two descriptions of things, and this allows us to start to look at, hey, what sort of spatial separation would we need, given that we have a certain area and a certain potential difference that we're going to apply across the sheets to have a certain capacitance. And that comes into play with actually building a capacitor with a certain capacitance. Again, by definition, that's the charge per unit potential difference. Higher capacitance of a capacitor, the more charge it can store per unit potential difference. That's the more energy it can store as well. So, capacitance is, so we want to look at the SI units. Capacitance has units of, oh, it's easiest to look at this and say, oh, it has charge per unit potential difference. So coulombs per potential difference has units of volts, coulombs per volt. So we've got that, that's C per V. And what do we do with that? Well, we call 1 coulomb per volt is equal to 1 farad. We use capital F for. So we talk about capacitances of capacitors measured in farads. Michael Faraday was an awesome physicist and did lots of stuff for electrodynamics. Nonetheless, there we go. We quantify capacitance in units of farads, which traces back to coulombs per volt, which has the idea of potential energy, stored energy, volts, right? Volts. All right, so that's what we've got for defining capacitance. What we want to start doing is ultimately charging one up, seeing how we charge it, and then sticking them in circuits in different configurations and seeing what happens. So that'll be next, but this is it for right now, and yeah, that'll do. That'll do. Be well. You have the capacity. You got it.